In question 22, you're being asked to figure out which table is going to best suit the case that we're talking about here. And what we're looking at is, well, it's going to be a whole bunch of options here, as you can see. I'm only showing you a few of them here on this page, but you can see it gets cut off at the bottom. I'm just going to show you a picture here that will best explain exactly what's going on with this reaction. So let's draw some pictures here. So initially, the situation will be that you'll have a buffer which is going to consist of A minus and AH. And then you can add either, it'll be OH minus, as it is in this case, or H plus. Now if we add OH minus, what's going to happen is that the OH minus will react with the AH according to this reaction, and produce A minus and H2O. So what I'm going to do here is have this react with one of these AHs here. And after it's reacted, that's all that's left in the solution. So let's take the other approach here. We'll start off with a buffer. We'll add H plus, and the reaction that we're going to use there is going to be a little different. It'll be A minus plus H plus will give AH. So what's going to happen is the H plus is going to react with the A minus in the solution, and we'll end up with that. So AH, and A minus. So the point of all of this is that after the OH minus or the H plus has reacted, all that's left in the solution is just A minus and AH. Now at that point, once you've got to this point where there's just A minus and AH in the solution, the OH minus and the H plus are completely gone. They're both going to be subject to the same kind of reaction, and that is AH can separate into A minus and H plus, but only a very small number will do so. So what can happen here is that the AH that's left here can separate into A minus and H plus, and you'll notice that the effect of that is that the A minus goes up and the H plus goes up, but the AH goes down. And exactly the same thing's going to happen in this situation. So I'll take an AH, I'll split it into A minus and H plus. And again, you'll notice that in this case the AH goes down and the A minus ends up going up and the H plus also goes up as well. So it doesn't matter about whether OH minus or H plus was added at the very beginning. In the end, the only thing that's happening here is the AH is separating into A minus and H plus, and even then it's only a small amount of it is doing that. So what's that mean to us as far as the table goes? Well, I'll select this and I'll get rid of some of this so we can have a bit more room. So what's happening is that we have our reaction, which in essence is really just the AH here going to A minus and H plus, because that's all that's happening in the solution. So the initial and the equilibrium, and initially we're going to have a certain amount, which I'm calling X. That's going to be the concentration at the beginning, or directly after the reaction of H plus and OH minus. And this will be Y. and 0 will be H plus, because that's because the AH hasn't split apart yet. Now afterwards, the AH goes down in concentration because it's splitting apart. The A minus goes up in concentration because it's becoming that. And the H plus goes up by the same amount as the A minus goes up. So you can see here, for every AH that splits apart, that's going to be minus delta. And for every AH that splits apart, we get a plus delta on the A minus and a plus delta on the H plus. So you just have to choose the option that matches what I've got here, and it's going to be for both cases, whether we've added sodium hydroxide or H plus to the solution initially.